Welcome back. We are continuing our unit today on hypothesis testing. And today we're actually going to do some problems. We're actually going to take some of what we've learned and do something with it. We're going to do 3 problems today, and I'm going to take you from the first step, stating the null and alternate hypothesis, all the way through to the last step, calculating, doing the math, arriving at a decision. Before we begin, we're going to need a formula. The formula for hypothesis testing for the mean in large samples looks like this. Z equals x bar minus mu divided by the standard deviation divided by the square root of n. So let's just remember what each of these things is. So x bar, that's the sample mean. Mu, population mean. Sigma is the standard deviation, and n is the sample size. Here we go. Mr. Saunders thinks Mrs. Saunders eats too much ice cream. He claims that she eats more than 5 gallons of ice cream every month. Mrs. Saunders disagrees and keeps track of how many gallons of ice cream she eats for 3 years. She finds the mean during those years to be 5.06 with a standard deviation of 0.25. At the 0.5 significance level, is there evidence for Mr. Saunders' claim? So let's pull up our 5 steps and we're just going to start filling them in. First, we're going to state the null and alternate hypotheses. Mr. Saunders claims that Mrs. Saunders eats more than 5 gallons of ice cream a month. So that's going to be our alternate hypotheses because there's no equal sign in it. Mu is greater than 5. That means the null hypothesis is mu is less than or equal to 5. We're going to do the 0.05 significance level. And the test distribution. If we look at the alternate, it looks like we're doing a z distribution, right-tailed test. Next up is the decision rule. We're going to use p-values. If p is less than or equal to 0.05, we'll reject the null. If p is greater than or equal to 0.05, we'll fail to reject the null. So now we'll go back and look at the problem and see what information we have. We have a sample mean of 5.06, population mean of 5, standard deviation of 0.25, and the sample size is hiding right here. I'll show you how that works in just a minute. We're going to plug all this into our formula, 5.06 minus 5 divided by 0.25 divided by square root of 36. Now, where did that come from? Mr. Saunders was claiming that Mrs. Saunders eats more than 5 gallons of ice cream a month. So that 3 years is 36 months. That's our sample size. Now we just plug this into the calculator to find the area under the curve above the z value that we just found of 1.44. So we have normal CDF, lower bound of 1.44 to an upper bound of 100 or 1,000, and we get the area under the curve, or the probability, to be 0.074. Now we compare that to our decision rule. And since p is greater than 0.05, we'll fail to reject the null. If we're failing to reject the null, we're accepting the null. But what does that mean? We need to be able to put it into English or into a sentence. And what this means is that, well, Mrs. Saunders eats less than or equal to 5 gallons of ice cream a month. Mr. Saunders was wrong. Let's try another one. In an advertisement, a grocery delivery service claims that its mean delivery time is less than 29 minutes. A random sample of 39 delivery times has a sample mean of 27.9 minutes and a standard deviation of 3.4 minutes. Is there enough evidence to support the claim at alpha equals 0.01? Again, we'll start with our hypotheses. It says less than 29 minutes, so less than is going to go in our alternate hypotheses. And then greater than or equal to will go in the null. Our significance level is 0.01. And our test distribution, we're in the z, and it's a left-tailed test. Now the decision rule. If p is less than 0.01, because that's our significance level this time, we'll reject the null. If p is greater than 0.01, we'll fail to reject the null. And now let's see what information we have. Sample mean of 27.9, population mean of 29, 3.4 is our standard deviation, and 39 is our sample size. So if we plug all that into our formula, 27.9 minus 29 divided by 3.4 divided by the square root of 39, we get a z-value of negative 2.02. Now we need to find the area under the curve to the left of negative 2.02, and we find that to be 0.021. Now we compare that to our decision rule. And so since p, 0.021, is greater than 0.01, we will fail to reject the null, meaning we accept the null. And now let's put that into some sort of English explanation. The delivery times could be more than 29 minutes. Last one. A nutritionist claims that the mean lobster consumption by a person in the US is 2.1 pounds per year. A random sample of 67 people in the US shows that the mean lobster consumption by a person is 1.9 pounds per year with a standard deviation of 0.82 pounds. At alpha equals 0.05, can you reject the nutritionist's claim? Well, she claims that the consumption is 2.1 pounds per year. That means that's going to be our null, mu equals 2.1, and our alternate is mu does not equal 2.1. We have a significance level of 0.05. Test distribution, we finally get to do a two-tailed test. And our decision rule, if p is less than 0.05, reject the null. If p is greater than or equal to 0.05, we'll fail to reject the null. And now we calculate, so we've got a sample mean of 1.9, population mean of 2.1, standard deviation of 0.82, and a sample size of n. So all that goes into our formula. When we calculate that, we get a z-value of negative 2. So we'll find the area under the curve to the left of negative 2, and we find that to be 0.023. Now, since this is a two-tailed test, we need to double that p-value before we put it into our decision rule. We get 0.046, which is less than 0.05, which means we're rejecting the null. We're rejecting the null, that means we think the alternate hypothesis is true, and in English, that means Americans likely do not eat 2.1 pounds of lobster per year. And there we are. 3 problems using our hypothesis testing method from beginning to end. We did a left-tailed test, a right-tailed test, and a two-tailed test. And you can see once you understand the different pieces and parts of hypothesis testing, it's really not too bad to put it all together. Thanks for being here.